Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with model diagnostics and that too the problem of heteroskedasticity. Like autocorrelation, heteroskedasticity is also a problem with respect to error terms. In the econometric modeling, we have dependent variables, we have independent variable, and that too independent variables explained and independent variables unexplained. So, independent variables unexplained is nothing but the error terms. Now, while using any kind of econometric modeling for the management decision or to look for the solution of a particular engineering problem. So, the model should be free from all these errors including this heteroskedasticity, and for that we have to first have the estimated model, get the error terms and then check the error terms whether it is behaving with respect to heteroskedasticity or it is in favor of homoskedasticity. So, corresponding to heteroskedasticity, the counterpart is called as a homoskedasticity. Homoskedasticity is good for the modeling, but heteroskedasticity is against the modeling. So far as decision making process is concerned and to look for the solution for a particular engineering problem. So, like autocorrelation, it is also step by step process just to connect with the theory, develop model, then must have data, then with the help of the OLS technique and the with the help of software, we can first get the estimated output, and after getting the estimated output, then use the estimated equation to have the error terms. So, now once you have the error terms, then we can check the heteroskedasticity issue. So, obviously, we are very much interested here to know what is exactly heteroskedasticity and how to detect this particular component, what are the regions through which heteroskedasticity can be a problem in the modeling environment, and what are the consequences if it is there in the system, and whether there is a kind of solution, and how will we go about this particular requirement to set the model which is free from all kinds of diagnostics. So, we start with the simple structure of heteroskedasticity. So, we have models, and then corresponding to models we have the error terms. So, the game is like this. So, let us see. So, first of all we start with like that what is exactly heteroskedasticity. So, hetero means this is different or something called as unequal, and its counterpart is called as homo, and that is nothing but called as same or equal. So, that means different or something called as same, unequal and equal. So, that is with respect to the error terms. So, that means usually once you have the estimated models, and from the software itself we can check the behavior of the error terms, that itself give the signal about the autocorrelation, and it also give the signal about the heteroskedasticity. Now, we are in the track of heteroskedasticity only, and even that plotting itself will give you some kind of exposure whether the error term behaves normally or some kind of as per the requirement of the modeling, or it is going against the modeling. So, obviously, with respect to error terms, where we are looking for actually covariance among the error terms, here in the heteroskedasticity we are looking for the variance of the error terms. For instance, let us start with the understanding like this. Let us we have 3 error terms u1, u2 and u3, and then we can create a covariance matrix with these 3 error terms. Then obviously, we can have 3 into 3 3 into 3 what we can call as a what we can call as error terms u1, u2, u3. So, that means we just represent column wise and row wise, then we will have a matrix like this. So, obviously, since there are 3 error variables, so obviously the variance covariance matrix with respect to all these 3 variables will be having 3 into 3 matrix, and then you will find the diagonal elements are error variance, that is what it is called as sigma square u1, then this is called as a sigma square u2 because the game is with respect to u2 and u2, and then sigma square u3. So, that is between u3 and u3. A rest of the place we will have actually covariance, that means technically u1 and u2, then it becomes sigma u12, and this is sigma u13, and this is sigma u21, and this is sigma sigma u23, then sigma u31 and sigma u32, and this is what the variance covariance matrix with respect to 3 error terms, and that can be extended with respect to k number of error variables. We have lots of interesting or additional models with respect to all these error terms, like arch model, Gauch models, all these things are there. We will discuss in details in the later stage, but in the meantime we need to understand what is the a error component, how what should be the behavior of the error term, and how to detect the heteroskedasticity. Then we will look for the kind of solution as per the particular requirement is concerned. So, here the entire matrix can be divided into 2 parts, which we have already explained in the case of autocorrelation. So, now we have 2 parts, one part is the diagonal elements, the other part is the off diagonal elements. So, off diagonal elements, so we have sigma u12, sigma u13 and sigma u23. Just this side it is nothing but transpose of these elements, that is nothing but since they are symmetric. So, that is why sigma u12, sigma u21 and sigma u13 and sigma u31, similarly sigma u32 and sigma u23, they are all almost all same. So, now when we are targeting sigma u12, sigma u13, sigma u23, then by default this problem will be going to autocorrelation. Now, we are looking for actually the variance of the error term, that is where actually sigma square u1, sigma square u2 and sigma square u3, and that too with respect to u1, u2, u3. So, what is exactly requirement for heteroskedasticity understanding is that, so the error variance over the cross sectional unit or over the time should be equal. So, that means technically, so the requirement of the modeling as per the OLS technique is that sigma square u1 equal to sigma square u2 is equal to sigma square u3, and simply you can call as a sigma square u. That is what the error variance, and what this is what it is called as homoskedasticity. So, we are looking for equal variance, and the requirement of the OLS technique for using any kind of decision making process is that error variance should be equal over the cross sectional unit and over the time. If they are different, then that will be automatically take you to the problem called as heteroskedasticity. So, if you say that what is homoskedasticity, homoskedasticity simply represents the equal error variance, and heteroskedasticity simply represents unequal error variance. So, that means technically if that is not the case, then heteroskedasticity, the typical heteroskedasticity will be the case for these 3 error variable, where sigma square u1 not equal to sigma square u2 not equal to sigma square u3, and by default it will take you the concept called as a sigma square uy. So, that means if they are not same, then they will create a kind of functions. So, now we like to check whether the error variances are equal over the time or they are unequals, and if it is unequal, and what is the level of unequal. So, that like the degree of autocorrelation. So, we have also the kind of understanding the degree of heteroskedasticity. So, we like to check what extent we can actually identify the heteroskedasticity problem, and what extent we like to solve this heteroskedasticity problem, so that the other diagnostic will be in the track, and the model will not be getting affected negatively, and that too we can use these models for the management decision making requirement. So, in the simple language, homoskedasticity means equal spread, that is the equal error variance, and heteroskedasticity represents unequal spread, that is to unequal error variance. So, now with respect to these understandings, so we will see how is this particular case. Okay. So, now we will move to this particular process like this. Okay. So, to summarize, the homoskedasticity represents the variance of the error terms, where sigma square u1, sigma square u2 up to sigma square uk, they are all same, and as a result we will simply write variance of error terms is equal to sigma squares, or expected value of square of the error term should be sigma square. That is what the requirement, and that is what the term called as homoskedasticity. This is good for the modeling. As long as error variance are same over the time and over the cross sectional unit, then we are in good track. When they are deviating from the various cross sectional units, or deviating from different time, then by default that is what is called as heteroskedasticity problem. So, by default heteroskedasticity definition in technically like this. So, variance of error terms should be sigma square I. So, it should not be sigma square u, because the moment we will say sigma square u means they are equal. So, when we are putting sigma square u I, so either you can call sigma square I, or you can call we can call sigma square u I. So, that both are same, just you have to understand accordingly. So, or expected value of square of the error term should not equal to sigma square u only, it should be sigma square u I. So, when we write sigma square u I, that clearly indicates that all the error variants are not equal. So, they are unequal, and when they are unequal, then that is what the problem is all about, and that is what the problem is called as heteroskedasticity. And this is one of the biggest virus in the modeling setup while looking for a kind of solution for any kind of engineering problem, and that too with the help of engineering econometrics. So, this is what the generalized concept of heteroskedasticity. So, I will give you the kind of clarity what is more about this particular component and how we can actually go about it. So, again if you connect with Wallace requirement, that is what called as CLRM, classical linear regression modeling, and that with the help of Wallace technique to estimate the parameters depending upon the problem formulation and the data availability. And the simple understanding is that here variance of ut is equal to sigma square. If that is not the case, then it will be variance of ut is equal to simply sigma square I, and that clearly differentiate the understanding of homoskedasticity and the understanding of the heteroskedasticity. So, let us see how is this particular flow again to so far as detection criteria is concerned. Of course, we understand what is exactly heteroskedasticity, but ultimately we like to know more something more about this particular component, how to detect, and what are the ways you can actually check this particular component, and what are the regions through which it will be in the system. It may be due to actually a wrong functional form, or the kind of structuring of the model, and with respect to the data structures, it may be due to anything, but we like to track how it happens and what is the level of this particular problem. And once you identify the exact regions through which this problem is coming, then we can also equally look for the solution. Until unless you know the typical regions behind this heteroskedasticity involvement, so you may not actually look, come into a kind of perfect solution. So that's why clear-cut understanding must be required. And as a result, first we start with graphical inspections. Let's say there are two variables, income and consumption, and that's the macroeconomics problem. So here consumption absolutely depends upon income. So consumption absolutely depends upon income, which is nothing but here. So like C equal to beta 0 plus beta 1 y. C stands for consumption and y stands for, let us say, income. And we have as usual the error term. So we will go about, means the functional relationship between consumption and income is like this, and with the help of the data we will estimate the consumption function and have the beta parameters like beta 0 and beta 1, and as a result we will have actually estimated equation C cap, that is what is called as beta 0 cap plus beta 1 cap and that to y. So by default error will be removed in the process. This is the non parameter and this is the non parameters. Now if we will simplify, we will have now C series and we will have now C head series. That is what the actual consumption series and that is what the estimated consumption series. Now the difference between the two will give you the error terms. Now what we are doing actually, corresponding to income and consumption, we will derive the error term and then plot the error terms and check whether actually it follows homoskedasticity pattern or it follows the heteroskedasticity pattern. So now if we will check here in this graph, and with respect to a particular data set and the particular estimated model, and we will find the error behaviors are little bit close each other. So when they are little bit close each other and within a particular small interval, and as a result it gives indication that it is the issue of homoskedasticity, and that is good for the modeling requirement or the modeling structure. If it is deviating, maybe the spread is very high towards up or towards down or in the left skewed or right skewed, then by default this will give it the indication that it is the heteroskedasticity involvement. So means plotting the error term itself will give you the signal whether the model is correctly specified or model needs some kind of diagnostics to correct the kind of requirement. So that means obviously, so first requirement is to check the behavior of the error terms and then get to know what is the level of this particular flow. So the other way you can represent in a 3-dimensional framework. So that is what y and x and then the error behaviors. You will find if you say equal spread and you plot these error terms, you see here the structure of this error plotting, and that too with a normal distribution. You will find the curve is actually more or less actually same. So they are very much converging each other. So as a result it gives the signal that it follows the normal distribution pattern, and when it follows the normal distribution, then by default that will be appearance of the homoskedasticity. So in short, the error term should follow, u should follow normally distributed with the mean 0 and the unit variance. That is what called as 0 1. So the behavior of the error term should be like this when we use OLS to have the estimation and use this estimated out for any kind of modeling decision and as per the engineering requirement. So you should follow 0 mean and unit variance. That is what the requirement. If not, then there is a problem, and that too when there is a question of heteroskedasticity, then the variance should not be unit or equal, it will be unequal. It will give you some kind of different patterns or some kind of functionality. Our job is to reduce this kind of functionality, because the error terms and that to the explained independent variables there in the independent clusters basket, they should not form some kind of problematic like the relationship among them, and then there should not be high volatile among them. So, if that is the case, then what is happening, it goes against the blue theorem, that is what called as best linear unbiased estimators. So, that means the parameter which will have, they have a simply a large variance, large standard errors, and as a result the significance of the particular parameters and the particular variables will be getting affected, and as a result it will go the model will go against the kind of specification test, goodness fit test, and overall the reliability of the models will be getting affected, and as a result we cannot use this model for the decision making process. This is the simple kind of understanding in the first instance. So, this is what the homoskedasticity look, and if you go for heteroskedasticity look, let us see here. This is one way of plotting, where if you compare the plotting of these ones, you see here the points are very close to each other with the estimated line, and as a result if you plot in a three-dimensional picture, then the behavior of these error terms are close more or less normally distributed, and they look very similar, and as a result it gives clear indication that there is the homoskedasticity. Now, if you look here, initially these points are little bit converge each other or close to the estimated lines, then after a particular point of time. So, like here if you see here, after this point of time there is a spread actually. So, they are diversifying here and there. So, as a result, so this gives the clarity that there is some heteroskedasticity problem, and that too up to a certain point it is it looks like homoskedasticity, and after that it gives like heteroskedasticity. So, that means clearly indicates that data itself, the level of data itself bring you the issue of homoskedasticity and heteroskedasticity. For instance, if you build a models up to this point, this much of data, let us say the entire data point is say 100 and this will be up to 80 and the rest is 20%. So, now if you build a model with respect to 80% of the data with respect to this plotting, then there is a high chance this will give you homoskedasticity picture. Now, if you club the entire data, then this will give you the heteroskedasticity pictures. So, in this case without any further discussion, the one way to have the solution is either you will normalize the data, or else you can divide the data into two different groups, and then estimate the model separately, and then check what is the validation or the functional relationship between these two. So, this is another way of looking to this model to look to have the better solutions as per the particular requirement. So, obviously, so this is what the kind of requirement, and then all right. So, now if you see here there is variations, now the same inspection can be observed with this particular diagram. This is the three-dimensional plot, and here you will see. So, the plots are actually little bit up, then down and then down like this. So, that means the look of these curves are not very much similar. So, this gives the signal that there is a heteroskedasticity. For instance, very simple here. So, if you will simply compare these ones like this curve, and then these diagrams, this one. So, you see here they are actually look like very similar, but if you look here they are very what we can call as completely different way altogether. They are not at all similar. So, that means they are deviating one differently from time to time, or sample to samples. That itself gives the signal that this case there is heteroskedasticity, and this case there is a homoskedasticity. That is the two different basket altogether. And by the way, if we are in the track of homoskedasticity, we are in good movement, and when we are in the heteroskedasticity side, then we are in the bad movement. So, as a result, we need to actually transfer the molding structure or restructure the entire setup, so that we should be in the track of homoskedasticity. Then you will go ahead with the prediction forecasting or something like that as per the particular requirement. Okay. So, this is what the case, and now this is another kind of heteroskedasticity loop. So, of course, the points are little bit means little bit deviation here with respect to error terms. They are not very close to the estimated line, but what is the best part of this particular plotting is that they are in a kind of confidence intervals, right. So, if of course, any kind of plotting, even if they are big spreads, still we can have a confidence interval. But now the confidence interval should not be very high while detecting in the issue of heteroskedasticity in comparison to homoskedasticity. So, there should be actually spread, but that spread should not be so deviating in nature. So, it should be very close. So, that means standard deviation should not equal to 0, standard deviation should not be very high, that too with respect to error term, and standard deviation should be very close to or very low, then this will give you the better judgment or better indication while using the kind of requirement. Okay. So, that is what the case, and so we will see how is the further behavior. So, this is another look actually heteroskedasticity. This is another loop, and that means the first one is in a kind of movement that in a kind of linear angles, and the previous one is a kind of increasing kind of spread, and that means it is a kind of positive spread, and this is a kind of negative spread, that means declining kind of movement. So, initially this spread is very high, and then over the time the spread is slightly actually low and low. So, that means this is good movement altogether, but this becomes bad movement, because initially the spread is very low, over the time it is very high. Okay. And by the way, it is not in your control, because when you are dealing with multivariate problem, there are many variables. Initially they are very stable, then over the time there is a instability because of certain regions or external factors. So, as a result, so the spread will be cannot be actually constant. The spread will be, you can say very much different over the time, or over the kind of cross sectional units. So, now this is actually the first one is the increasing kind of spread over the time, and this is the decreasing kind of spread over the time. But by the way, both the cases there is a heteroskedasticity, and we should look for that. That means technically we should quantify it and test it, like multicollinearity and autocorrelation. So, we check whether the particular heteroskedasticity problem is statistically significant or not. If that is the case, then we cannot just go ahead. So, we look for the kind of solution, and then we need the declaration that this problem is free from heteroskedasticity. But it is very difficult to completely clean this virus, but at least it should be in the tolerance level, like this issue of multicollinearity and the issue of autocorrelation. So, that is the case actually. So, now if you ask me how you can go about this kind of movement. So, the first one is the graphical check, and where you just start with the step by step process, build the models, connect the data, use the software, have the error terms, then plot this error term, that is what the residuals. Then we will get to know how is the kind of movement with respect to error term, and that too with this problem in terms of income consumption relationships technically. Okay, so these are all various requirement. So, now means after knowing the kind of initial inspections, So, we can actually come to the kind of conclusion about the consequence. If you say that it is a virus, so what is exactly the impact or the kind of incidents? The consequence, of course, is not so good. It will largely affect the model reliability, which I have already clearly highlighted in the classical linear regression modeling. If you connect with Gauss Markov theorem, that is the blue theorem. So, we need actually the parameters should be completely unbiased, they should have a very minimum variance, and then the parameters should be very consistent. So, unbiasedness, minimum variance, and then the kind of consistency, or sometimes we can use also sufficiency, but sufficiency criteria is not required here. So, we need actually three things while checking this kind of diagnostics. So, parameters should be completely unbiased, and they should have a very minimum variance, and they should very consistent over different point of time or different cross sectional unit. Now, what is happening in the case of or in the presence of heteroskedasticity? So, the parameters will not follow the blue theorem. So, they may not actually means they may follow some items, but they may not follow the other items. For instance, having actually heteroskedasticity, the parameters will be still unbiased and consistent, but it will not give you the minimum variance, rather it will increase the variance factors. As a result, standard error will be very high, and what is happening, the parameters will be not statistically significant, even though they are unbiased and consistent. That is what the actually game is all about, heteroskedasticity. So, that means when these viruses are there, like multi-coordinate heteroskedasticity and autocorrelation, then our parameters or the estimated models in overall setup is not okay to proceed for the forecasting or the decision making, or as per kind of implication about any engineering problem. So, now this is what the consequence, simple understanding of heteroskedasticity and the behaviors, and then we will look for the kind of solutions. So, means technically graphically we inspect and have the kind of solutions, and means solution about the homoskedasticity or heteroskedasticity, and then of course, so far as the consequence is concerned, in the case of homoskedasticity, so they will follow all the criteria, like they are unbiased, they are consistent, and they are also follow the pattern called as minimum variance. But in the case of heteroskedasticity, the parameters will be still unbiased and then consistent, but they cannot follow the minimum variance. That is what the, and that too the minimum variance is one of the most important requirement of the blue theorem. If that is not the case, then this will largely affect the kind of systems. That is why we need actually clean models which can give the better solutions as per the particular requirement. With this we will stop here, and we will continue these lectures in the next class. Thank you very much.